In today's lecture of automobile engineering, we are going to see another part from the automobile engineering. Let us understand what are the engine operations. You will ask why the engine operations are to be studied, because engine is the heart of an automobile, and when we consider engine performance, then it is the essential and crucial issue related to the automobile engineering. So today we are going to see the engine operations. IC engine and steam engine are the widest used internal combustion engines. Now, why internal combustion engines? Because they burn heavier oils of these types, and diesel engine in the widest use. Both IC engine and steam engines are basically heat engines and convert heat energy into mechanical energy. But IC engines are now widely used for the purpose due to some of the reasons. The standing uses in the field of transportation. In the many industries, farms, simplicity and low cost operation are the determining factors in the adoption of IC engines. The main difference between IC engine and steam engines we can point out and we can summarize as: in IC engines, the combustion of fuel takes place inside the engine cylinder, while in steam engine, the combustion of fuel takes place outside the cylinder. Due to high temperatures and pressures, materials having better resistance are required for IC engines. IC engines are single acting. Piston is directly connected to connecting rod. There is no piston rod and hence no stopping box. Steam engine requires a big boiler to store water for converting it into steam, and condenser to condense exhaust steam into water. But IC engines require only a small tank to store fuel, and there is no steam condenser in it. IC engines are easy and quick to start and stop. Steam engines take time in lighting the fire and generating the steam. IC engines are lighter and cheaper as compared to steam engine. So this was the brief introduction related to the difference between IC engine and steam engine. Let's move forward. We'll talk something about petrol engine, or it is also called as a gasoline engine. Now, the engine which gives power to propel the modern Indian automobile is petrol burning, spark ignition, 4-stroke cycle, internal combustion engine. Petrol is a liquid fuel and is called by the name gasoline in worldwide. That is why the petrol engines are also known as gasoline engines. The ability of petrol to furnish power rests on two basic principles of physics. I am sure you have heard about this in the internal combustion engine subject, but let us revise. And the two basic principles of physics are: burning or combustion is always accompanied by the production of heat. When a gas is heated, it expands. If the volume remains constant, the pressure rises according to Charles' law. The operation of petrol engine in the production of power may be described as follows. During the downward motion of the piston, the air-fuel mixture is sucked from the carburetor into the cylinder. During the upward motion, the mixture is compressed by the piston in the cylinder and ignited by an electric spark. The pressure exerted on the piston is transmitted through the connecting rod to the crankshaft that is made to revolve. The crankshaft turns through one half of revolution as the piston moves downward. A flywheel attached to the crankshaft stores up energy. The momentum of the attach to the crankshaft stores energy, and flywheel carries the piston through the balance of its motion until it receives another power impulse. In the 4-stroke cycle engine, the 4 strokes are named suction, compression, power, and exhaust in accordance with the operation of the cycle which occur during each particular stroke. The 4-stroke Otto cycle spark ignition engine, where suction stroke, during suction stroke, piston was moving downward and by the crankshaft, which is revolved either by momentum of the flywheel or by the power generated or by the electric starting motor. In the compression stroke of the Otto cycle spark ignition engine, the piston moves upward, compressing the charge. Ignition and much of the compression also takes place during this stroke. In the working, or it is also called as power stroke, or it is also called as the expansion stroke, the expansion of the gases due to heat of combustion exerts a pressure on the cylinder and piston. Both the valve remains closed during this stroke. And last, the exhaust stroke. During this stroke, the inlet valve remains closed and exhaust valve opens. The greater part of the burnt gases escapes because of their own expansion. The piston moves upward and pushes remaining gases out of the open exhaust valve. Only a small quantity of exhaust gas remains in the clearance space, which will dilute the fresh incoming charges. Therefore, in this type of engine, my dear friends, Four strokes of the pistons are required to complete the cycle, and the four strokes make two complete revolutions of the crankshaft. The operations are repeated over and over again in the running engine. Now, each alternative revolution of the crankshaft has one power stroke. So, my dear friends, this was the brief introduction of Otto cycle. Let's understand wall timing diagram of a four-stroke Otto cycle. Now, in order to understand the wall timing diagram, you should know what are its basic. Okay. As you know, in the Otto engine, inlet valve opens during the suction stroke and the exhaust valve opens during the exhaust stroke. The exact moment at which each of the valve opens and closes with reference to the position of the piston and crank can be shown graphically in the diagram. And that diagram is also called as wall timing diagram, or in capital it is called as VTD. What are the factors that are considered in the VTD, that is wall timing diagram, are, let's revise, that is IVO, inlet valve opens, then IVC, inlet valve closes, IS, ignition starts, EVO, that is exhaust valve opens, EVC, exhaust valve closes, TDC, top dead center, and bottom dead center. So these were the factors that considered under theoretical wall timing diagram. Okay, let's understand what exactly happens in actual wall timing diagram for a four-stroke Otto cycle engine. In the suction stroke, the inlet valve opens, the piston starts to move downward from TDC, that is top dead center, and reaches to BDC, that is bottom dead center position. The fresh charge of air-fuel mixture enters into the cylinder and the exhaust valve remains closed. In the next compression stroke, now we are moving from suction to compression, therefore both the valve remains closed. The piston starts to move upward from BDC, that is bottom dead center position, thus compressing the charge till it reaches to TDC, that is top dead center. We are moving to the third stroke, that is a expansion, or that is a working, or that is a power stroke. Remember, these three names are the common names for the third stroke, that is working stroke. Both the valve remains closed again, but sparking takes place from spark plug, which ignites the compressed charge, and now piston has set itself into a motion moving downward from TDC, that is top dead center, and reaches to BDC, that is bottom dead center. Last stroke of the first cycle, that is exhaust stroke. The exhaust valve opens, the piston moves from bottom dead center, that is BDC, and reaches to top dead center, that is TDC, thus rushing out the burnt gases from the cylinder. And at this position, the inlet valve remains closed. Dear friends, you have to understand the basic of this engine working, because in the form of four stroke, that is suction, compression, expansion, and exhaust stroke, the cycle gets completed. But in actual practice, the above cycle what we have discussed is slightly modified. The exact moments of opening and closing the valves with reference to the piston and crankshaft are somewhat changed, and that diagram is called as AVTD, that is actual wall timing diagram. The notes which you have received on the group have been included all these theory parts. The opening and closing of inlet and exhaust valves are described as follows. For the inlet valve starts opening at 10 degree to 30 degree before TDC and measured in degrees of crankshaft rotation. Now dear friends, this is what the engine operation is to be considered and is to be required. But when we consider the thermodynamical aspects of an automobile, it is an important to understand pressure volume diagram of four-stroke Otto cycle engine. What happens from point 1 to 2, that is exhaust and suction, from 2 to 3, that goes, then 3 to 4, 4 to 5. So you have to consider this pressure volume diagram, or it is typically called as a PV diagram for a four-stroke Otto cycle engine. Okay, we will move forward. Four-stroke diesel cycle, that is a compression ignition engine. Let's understand this. The engines of heavy motor vehicles like truck, buses, stationary power plants, big industrial units, and ships mostly operate on diesel cycles or constant volume cycle. Now it was introduced by Dr. Rudolf Diesel in 1897. Diesel cycle differs from Otto cycle in only one respect. The heat is added at constant pressure instead of at constant volume. Therefore, it comprises two adiabatic processes, one constant pressure heat addition process and one constant volume heat rejection process. Diesel cycle engines mostly use heavy oils. Diesel oils is the most common among these. In diesel cycle engines, only air is compressed in the cylinder to a high pressure. The temperature of this compressor becomes sufficiently high to ignite fuel. Diesel is injected in the cylinder at the end of compression stroke. Again, there will be 4-stroke diesel cycle compression ignition engine, and the 4 strokes will remain same, that is suction, compression, expansion, exhaust. For suction stroke, the piston moves down from top dead center position. Air will be sucked into the cylinder through the open inlet valve, which closes at the end of the stroke. The exhaust valve remains closed during the stroke. Compression stroke, the piston will move upward from bottom dead center position, that is BDC. Inlet and exhaust valves remain closed. The air will be compressed in the cylinder with the upward movement of the piston, and as soon as the compression ratio in the engine is high, that is in the range of 10 to 20, the air will be finally compressed to a pressure as high as 40 kg per centimeter square, or it is a 40 bar, at which is a temperature high up to 100 degrees Celsius will be achieved, enough to ignite the fuel. Next will be always the working stroke or power stroke or expansion stroke, and at the end of this compression stroke, the fuel is injected into the hot compressor where it starts burning and maintaining the pressure constant, and at the point 4 the fuel supply will be cut off. Now theoretically this fuel is injected at the end of compression stroke and injection continue till the point of cutoff. Meanwhile, the piston will move from point 3 to 4, and this stroke will be called as constant pressure stroke. Theoretically, the power stroke starts from point 4 and will be ending. The hot gases will expand and adiabatically to the point 5 in the cylinder. Now, moving to the exhaust stroke, the piston will move upward, the inlet valve will remain closed and the exhaust valve will open. The greater part of the burnt gases will escape because of their own expansion. The upward movement of the piston will push the remaining gases out through the open exhaust valve. The cycle will be completed like actual and theoretical PV diagram, that is pressure volume diagram for a 4-stroke. In figure 2.11 and 2.2. We'll continue the same series of lecture in the next. Till then, thank you.